Alright, this video is going to go over the colligative properties and practice some problems with them. This is for Advanced Chemistry 30S. Colligative properties are properties of solutions. They are properties that change when you make a solution from a solvent and dissolve some solute in it. But these properties, the magnitude of that change depends not on the nature of the solute, but rather on the number of solute particles present. For example, there's lots of things that change when you dissolve solutes in solvents. The color might change, but clearly the color of the solution would depend on the nature of the solute. Nickel solutes produce green solutions, copper solutes produce blue solutions. So color of a solution is not a colligative property. There are four basic properties that we're going to look at that are considered colligative properties. The first is the vapor pressure lowering. So when you have a solvent which is volatile, a solvent which evaporates, there's going to be a certain equilibrium vapor pressure above the solvent. If you dissolve in the solvent a non-volatile solute, a solute which does not evaporate, then the vapor pressure above the resulting solution will be lower than the vapor pressure that was above the pure solvent. So that's the idea of vapor pressure lowering. We looked at a phase diagram of this. If you consider a phase diagram for water, we know that it looks something like this. And we know there's a solid, a liquid, and a gas region. So if you dissolve some solute, non-volatile, in the water, then every point on this graph where there's a equilibrium vapor pressure between liquid and gas here, every point there would drop by a certain amount. So what you'd end up getting is a new curve that looks like this, which is below the old curve. Now notice that if we had on a phase diagram, this is pressure and this is temperature on the x-axis, if this was 1 atmosphere, then we know that's a special point on the diagram. If we go straight over, this point here, when we were on the original graph, was the solid-liquid phase boundary. At 1 atmosphere, if we went straight down, that would have been the normal melting point or normal freezing point of the substance. But by dissolving a solute and lowering vapor pressure, the substance is now going to freeze at this point. So the old freezing point was here, the new freezing point is over here to the left, so we see that there's been a drop in freezing point, and that leads to the second colligative property, freezing point depression. So freezing points are depressed, they drop when you dissolve a solute into a solvent. If you look at the boiling points, same diagram, go over to the right, and where the liquid-gas boundary is found at 1 atmosphere, if you go straight down to the x-axis, that would have been the normal boiling point of the liquid, of the pure solvent. But now, to reach the same point on the solutions curve, the red curve, we have to go a little bit further. So the boiling point has risen. So we see an increase in boiling point, but we see a decrease in freezing point. So we have boiling points elevated, raised, and we have freezing points depressed, lowered. There's a very similar equation that describes both of those. The change in the freezing point, measured as the freezing point of the solution minus the freezing point of the solvent, the change, we'll take an absolute value of that. It'll always be a positive number. That's equal to I times Kf times molality of the solution. The I is based on the solute. It's called the Van't Hoff factor, and it's based on the solute. If you were to dissolve a non-electrolyte is a solute which does not break apart into ions. So for example, a molecular compound, so something made of only non-metals like sugar, C12H22O11. So if you see something made of just carbon-hydrogen or carbon-hydrogen-oxygen, maybe some nitrogen, only non-metals, then you're dealing with a non-electrolyte, and for that, if you dissolve 1 mole of solute in the solvent, you'll have 1 mole of solute floating around in the solution. So I will be a 1 in that case. So for non-electrolytes, I is equal to 1, because dissolving 1 mole of solute produces 1 mole of dissolved substance. But what happens if you're dissolving an electrolyte? An electrolyte, another name for that, would be an ionic compound or a salt. There are also acids and bases, as we learn in grade 12 chemistry, but here we'll just consider salts as being electrolytes. When they dissolve in water, they break apart, they dissociate, they ionize. For example, if you dissolve a mole of sodium chloride in water, you'll get a mole of sodium ions and a mole of chloride ions. So 1 mole of sodium chloride actually produces 2 moles of ions. In the same way, 1 mole of potassium nitrate, KNO3, would produce 2 moles of ions, a mole of potassium ions and a mole of nitrate ions. So in salts like this, the effect is going to be doubled that of a non-electrolyte, because you get 2 moles of particles for every 1 mole of solute. So for these guys, the Van 't Hoff factor would be a 2. If you consider a salt like calcium chloride, CaCl2, or perhaps sodium sulfate, Na2SO4, notice now that for both of these examples, 1 mole of the salt produces 3 moles of ions. 1 mole of calcium chloride would give you a mole of calcium and 2 moles of chloride ions for a total of 3 moles. A mole of sodium sulfate would give you 2 moles of sodium ions and 1 mole of sulfate ions, again a total of 3 moles. So because you get 3 moles of ions for every 1 mole of solute, I here is equal to 3. Now in reality, the Van 't Hoff factor is usually a little bit lower than what we're saying here because of a phenomenon called ion pairing. In water, you don't really achieve 100% dissociation. Sodium ions and chloride ions in salt water will occasionally bump into each other and recombine to make NaCl. So where we would expect to see an I of 2, you might actually see a Van 't Hoff factor of 1.9 or 1.95 for sodium chloride. In sodium sulfate, same thing, there's positive sodium ions, negative sulfate ions. You might occasionally have sodiums and sulfates bump into each other as they float around in the solution and recombine. The fact that sulfate has a greater charge, -2 instead of -1, means that this might actually be larger effect. So instead of 3, you might end up seeing 2.8 or 2.85 or something like that. We will always assume, unless the question says otherwise, that we have complete ionization. So in these cases, I would have been 2 or 3. So when you're dealing again with a non-electrolyte, a compound that is molecular, one that's got only nonmetals in its formula, I will be 1 because they do not ionize, they do not break into ions. If you're dealing with salts, you have to look at the number of ions in the formula to determine the value of the Van 't Hoff factor. The Kf is called the freezing point depression constant, technically the molal freezing point depression constant. It's based on the solvent. So every solvent has a different constant, and you would look those up in a data booklet, okay, or it would be given in a question. I've got our data booklet that we use in class, and here's a table of solvents, their boiling points, their Kb values, that's for boiling point elevation, their freezing points, and their Kf values, their freezing point depression constants. So each solvent has a different freezing point, boiling point, and constants for use in these formulas. And finally, the M is the molality of the solution. And you remember that molality, not molarity, but molality, is the moles of the solute divided by the kilograms of the solvent. Okay, so remember that. The boiling point elevation equation looks very similar. We've just replaced the F's for freezing point with B's for boiling point, but it's basically the same idea. Now I just realized that I overlooked the equation at the top here to describe vapor pressure lowering. That was based on Raoult's law. Raoult's law says that if you know the vapor pressure of the pure solvent, that's what this PA degree symbol means. The A is our solvent. If we were dealing with a real problem, we wouldn't just use an A, we'd use a more descriptive subscript. For example, water, you might say PW. The degree symbol there means the pure solvent. So this is the vapor pressure of pure solvent. Remember that the only thing that's evaporating is the solvent, because our solute is considered non-volatile. It does not evaporate. If your solute does evaporate, then it's a little bit more complicated than this, but we're not going to look at that. PA is the vapor pressure, again, of the solvent, but this time not pure solvent. It's the vapor pressure above the solution. So this time you've dissolved some of that solute. XA, we know, is the mole fraction, and the subscript A means of the solvent. So basically your mole fraction of solvent multiplied by the pure solvent's vapor pressure gives you the vapor pressure of the solution. Since the mole fraction is always less than 1, the vapor pressure above the solution will always be less than the vapor pressure above pure solvent, which is why we have vapor pressure lowering. The last colligative property is called osmotic pressure. And this one harkens back to biology class, I'm sure, the idea of osmosis. To understand it, let's just consider for a moment a situation where you have a U-shaped tube like this. And in this U-shaped tube, let's put a semi-permeable membrane. A membrane that is permeable to water, but not to any other solute, for example, sugar or salts and things like that. Only water is allowed to pass through this membrane. On one side of the membrane, let's put pure water, pure H2O. On the other side, let's put sugar water, so water with some sugar dissolved in it. Now, because there's a higher concentration of sugar on the left than on the right, we know that there's a concentration gradient. We could represent that with a sort of like a seesaw. There's a high concentration of sugar on the left. There's a low, in fact, 0 concentration on the right. So there's this gradient, this slope like this. The situation is unstable, and over time the system would like to achieve equal concentrations on both sides. Now, if there was no membrane, then diffusion would happen, and sugar would simply diffuse over to the right, and then the high concentration would drop, the low concentration would rise, and the gradient would disappear. However, that membrane prevents diffusion. So what's going to happen instead is that the water will, by osmosis, travel like this across the membrane. You'll go from an area of low concentration of solute to an area of high concentration. So that would make the higher concentration area more diluted. It would lower that concentration. And if there was let's say there was a less concentrated sugar solution here, as water escapes, that less concentrated solution would become higher concentration, and so this would rise. Now, over time, as water continues to travel through the membrane, this meniscus is going to rise. So let's say it goes up to here. The other meniscus is going to drop. So let's say it goes down to there. Now, as you get this difference in height between the two sides, that delta H, this starts to remind us of a manometer from our gases unit. There's going to be a difference in pressure. Eventually, that pressure difference will stop the osmosis from occurring. Basically, it will reach an equilibrium state where for every water molecule that passes through by osmosis, another water molecule, because of this pressure, will be forced back through the membrane. And so you reach an equilibrium state where the two levels here stop changing. Now, if you were to apply pressure like this and return this to the original system, or apply that pressure at the beginning to prevent the osmosis from even beginning, the pressure required to prevent the osmosis from happening in the first place is the osmotic pressure of the solution. Okay? The equation for osmotic pressure is simply based from the ideal gas law, surprisingly. PV equals nRT. If we divide both sides by volume, we get P is N over V times RT, but N over V is moles divided by liters, which we could call concentration. So there's another form of the ideal gas law. Since this applies to gases, let's use a different symbol for osmotic pressure. Instead of the letter P, we'll use the Greek letter for P, which is the letter pi. Usually it's a capital pi, which looks like the lowercase, just a little bit bigger. And because our solutes may be ionic, they may be electrolytes, we'll throw in the Van Hoff factor here again. So the pi equals I CRT, where C is the molarity, moles per liter, of solute. T is temperature, as always, in Kelvin, and R is the ideal gas constant. Now we remember when we use the ideal gas law, we can use either 8.314 or 0.0821 as our values for R, but if we use this value for R, we get kilopascals in the pressure. If we use this one, we get atmospheres in the pressure. So keep that in mind. Alright, there's enough background. Let's jump in and start solving some problems. If you want to pause the video and try the problem yourself, that would be a good thing. If you're not really sure how to do it, then just follow along with me. So the first question, what is the freezing point of a solution? That very phrase right there tells me that we're in the solutions unit, we're dealing with colligative properties, and almost certainly the freezing point depression is what we're dealing with. So what's the freezing point of the solution made by dissolving 5 grams of naphthalene? Naphthalene is my solute in 500 milliliters of carbon tetrachloride. So this is my solvent. Keep that in mind. We know the density of the carbon tetrachloride. We know the carbon tetrachloride normally freezes at minus 22.99 Celsius. And we're given its molal freezing point depression constant, Kf. So the first thing I'll do is I'll just write out the formula for the freezing point depression. Delta Tf was equal to I times Kf times molality. Now molality, we remember, is moles of solute per kilogram of solvent. So let's rewrite this as I times Kf times moles. Now instead of just saying solute, let's say moles of naphthalene. I'll say moles of C10H8 over the kilograms of the solvent, but our solvent is carbon tetrachloride, so CCl4. So I just replaced molality with moles of solute per kilogram of solvent. But we know that moles can be represented as mass over molar mass. So we could actually say that delta Tf is equal to I times Kf, and instead of moles of naphthalene, we could say mass of naphthalene divided by the molar mass of naphthalene. That's going to give us the moles of naphthalene, and then we still have the kilograms of CCl4 in our denominator as well. So there we've got sort of an exploded version of the freezing point depression equation. And if we look at this now, we can ask what's the value for the Van Hoff factor? Well, that's based on the solute, and our solute was naphthalene. Naphthalene C10H8, that looks like it's made of only nonmetals, carbon, hydrogen, and so this is going to be a non-electrolyte. Remember, to be an electrolyte, you have to be a salt. You have to have ions in your formula. Again, in grade 12 chemistry, we'll look at acids and bases as also being electrolytes, but for now, we'll consider only salts as electrolytes. So because naphthalene is a non-electrolyte, the value for I will be a 1. It does not break into ions. The Kf value, we know, it was told in the problem, is 30.0, and that's the Kf value for our solvent, carbon tetrachloride. We know the mass of naphthalene that we used, it was 5 grams. The molar mass of naphthalene, we can just grab a calculator, periodic table, and evaluate that. So we have C10H8, so 10 times 12.01 plus 8 times 1.01, 128.18. And I'm being a little lazy with my units here, but the formula is right above, so I think the units are straightforward. This will be grams per mole. And then the kilograms of the carbon tetrachloride, kilograms of solvent. The question said we had 500 milliliters of carbon tetrachloride. That's not kilograms, but we know the density. So we could just go do a little grade 9 math calculation. I'll do that here on the side. We have 500 milliliters. We can convert milliliters to grams using the density, and then we can convert the grams to kilograms. Okay, there's 1 kilogram is 1,000 grams, and the density was 1.59 grams per milliliter. So 500 milliliters times 1.59 divided by 1,000 is 0.795 kilograms. So 0.795 kilograms, and that was of the naphthalene, right? C10H8. All right, so now we can evaluate delta TF. We can calculate the change in the freezing point. So with our calculator, we'll go 1 times 30 times 5, and then divide that by 128.18, and divide again by 0.795, and we get 1.47 degrees Celsius. Notice that because it's a change in freezing point, we actually could have used either Celsius or Kelvin. Change in freezing point would be the same in either unit. If the temperature went up by 5 degrees, it also went up by 5 Kelvin. Now I just realized my significant digits here, I've got an extra digit because our mass had only 2 significant digits. This should really be 1.5 degrees Celsius. Alright, so the question was not to find the change in the freezing point. We wanted to know what would be the freezing point of the solution. Well, freezing point of the solution is going to be lower than the freezing point of the solvent, of the carbon tetrachloride. Carbon tetrachloride's freezing point is minus 22.99 degrees Celsius. So we can say here for the solution, okay, let's calculate its freezing point. We'll start with the freezing point of the carbon tetrachloride, minus 22.99 degrees Celsius. We're calculating the freezing point of the solution. And because the concept is freezing point depression or lowering, we'll subtract this change that we just calculated, 1.5 degrees Celsius. So minus 22.99, take away 1.5 is going to be minus 24.5 degrees Celsius. There is the freezing point of our solution, which is 1.5 degrees lower than the freezing point of pure carbon tetrachloride. A second example, I see a KF value in the question. I see the phrase freezing point, so I'm getting comfortable now. This is a freezing point question, but let's jump in. What mass of sodium nitrate should we dissolve in 25 mils of water so the resulting solution freezes at minus 6 degrees Celsius? And we're given the KF value for water. So this question sort of reverses things a little bit. We know what the final freezing point of our solution should be. It should be minus 6. So why don't we calculate what the change in freezing point was? Since we know the freezing point of the solution, we can calculate the change by taking the absolute value of the freezing point of the solution minus the freezing point of the pure solvent. Okay, just a straightforward way of finding change in anything, right? So that's going to be minus 6 degrees Celsius, take away 0 degrees Celsius, and the absolute value of that will be 6.0 degrees Celsius. In other words, we wanted a freezing point that's 6 degrees lower than the original freezing point of water. So this delta TF of 6 degrees we can put into our formula, which again was I times KF times molality. And I'm going to jump right to the exploded version of this equation that we just used, is equal to I times KF times mass. Now our solute in this question was sodium nitrate. So mass of sodium nitrate over molar mass of sodium nitrate. Mass over molar mass is moles of solute. And then also divided by the kilograms of solvent, which in this case is water. Alright, now the question is what mass of sodium nitrate should be dissolved. So we're looking for this variable, the mass. So now that I've got this equation, we could simply rearrange it. Let me just go back and call this delta TF. So we can rearrange it and we can say that the mass of the sodium nitrate is delta TF times molar mass of sodium nitrate times kilograms of water divided by, I'm just doing algebra, this times the denominator here equals this numerator, and then we're going to have to divide by these two things to get the mass by itself, so divided by I and KF. Now we can plug our information in. We know delta TF is 6 degrees Celsius. The molar mass of sodium nitrate, we'll just quickly evaluate that. We have 22.99, 14.01, and 3 times 16, 85 grams per mole. The kilograms of water, we had 25 milliliters of water, so let's go back and evaluate that. 25 milliliters will convert milliliters to grams, and grams to kilograms. There's 1 gram per milliliter, that's the density of water, which wasn't stated but which is assumed that you know, the density of water. There's 1,000 grams per kilogram. Now we're 25 milliliters divided by 1,000 then is 0.025 kilograms. Now what's the value for I? I again is the Van Hoff factor, which comes from the solute, and our solute is sodium nitrate, which is clearly a salt, an ionic compound, and it has just 2 ions, Na plus and NO3 minus. Therefore I for this salt is going to be 2. So 2, and in the KF value 1.86, which is the KF value for water that we were given in the question. So now we'll just grab our calculator and evaluate this. The answer is going to be a mass, so it's going to be grams. Mass over molar mass is where that came from, and we always use grams in that formula. So 6 times 85 times 6 times 85 times 0.025, divide by 2, divide by 1.86. We need 3.4 grams of sodium nitrate. So a solution with 3.4 grams of sodium nitrate dissolved in 25 mils of water should freeze at -6 degrees Celsius. Let's do one more of these problems, and I'll end this video and we'll start another one in a few minutes. A student dissolved 10 grams of an unknown non-electrolyte solute in 100 grams of benzene, benzene's formula C6H6. The resulting solution had a boiling point of 81.5 degrees, where benzene normally boils at 80.1 degrees. We know the boiling point elevation constant for benzene is 2.53. What's the molar mass of the solute? So I hope you can understand this is a boiling point elevation question, so delta TB is equal to I KB times molality. And let's again explode that molality, so delta TB is I KB moles, which is mass over molar mass. So mass of our solute, which we don't know, it's an unknown, so I'll just say mass of X over molar mass of X. Mass over molar mass is the moles of the unknown solute, and then divide that by the kilograms of solvent, which in this case is the benzene C6H6. Now, do we know the change in boiling point? Well, we look and we notice that benzene normally boils at 80.1, but our solution boiled at 81.5, so delta TB is the absolute value of that difference, 81.5 minus 80.1. So it's going to be a difference of 1.4 degrees Celsius. So delta TB is 1.4. Do we know I? Well, we were told that the solute is a non-electrolyte, which means it doesn't dissociate, so I is equal to 1. Do we know the mass of the solute? Yes, we do. It was 10 grams. And the kilograms of the solvent, it was 100 grams of benzene, which is 0.1 kilograms. So we have enough information to go find the molar mass. The molar mass will equal I times Kb times the mass of the unknown divided by delta Tb and the kilograms of the solvent, C6H6, is equal to 1 times 2.53 times 10.0 divided by 1.4 and divided by 0.10. So that's going to be equal to, let me just grab a calculator, 1 times 2.53 times 10 divided by 1.4 and divide by 0.1, we get a molar mass of 181 grams per mole. It's got probably one extra digit there. 1.8 times 10 to the 2 would be a better way to say it, grams per mole. Just realize I'm a little off the screen there. So there's a simple, common way to find the molar mass of an unknown solute through boiling point or freezing point changes.